Okay, welcome back to Math 160. We left off on page 8 of our Unit 3 notes. So we're going to now talk about measures of variation. So let's scoot over to our page 8 and take a look. So let's start off by talking about what measures of variation are. So variation is the measure of how spread out or how dispersed the data is. Measures of variability or measures of variation. Measures of variation, measures of variability, same thing. Measures of variation include standard deviation, variance, and range. Variation is a measure of how spread out or how dispersed the data is. Measures of variation include standard deviation, variance, and range. We talked about range last time. We referenced the fact that range has to do with your high value and your low value, and then trying to determine how spread out the data is between those two. So I'm going to skip forward to where it says formula, and I'm just going to write H minus L. So it's your high value for the entire set of data minus the low value of the entire set of data. So for our definition, the range of a data set is the difference between the maximum and the minimum of the data. Of your data set. Okay, the range of a data set is the difference between the maximum and the minimum of your set. Sometimes it's nice reading the definition in words before you see the actual formula and vice versa. Lastly, we have the variance for measures of variation. The variance of a data set or that's fine. I just had to reread what the hell I wrote. I wrote something very strange. The variance of a data set is equal to the square of the standard deviation. There are some key points about variance that are actually really important to note. And you will understand how to calculate variance after we go through the process for calculating standard deviation. You find variance along the way, meaning it's the last step prior to finding the standard deviation. And I'll show you what I mean by that. We should note that variance can only be positive or zero. Okay. The notation for variance for a sample is actually S squared. S squared is the notation for variance because it's the square of the standard deviation. So that means S, lowercase, is standard deviation. I'm going to note that here again. So S squared is variance. S is standard deviation. Out of curiosity, mathematically, how would you go from an S squared to an S? What operation would you perform mathematically to make that happen?
Square root.
Perfect. So if you were to square root S squared, you would get S by itself, wouldn't you? That's kind of hinting at the fact that once we calculate the variance, you then take the square root of the variance to find the standard deviation. So that's why they're the same letter. This is why we use this notation to show that we can move from the variance to the standard deviation by simply taking the square root. You can jot that down in your notes at this point, but we will talk about that in just a second. I want to add one more note for variance. It can increase drastically with the inclusion of one or more outliers. Since it's a measure of variation, the spread of data, it should make sense that variance would increase that drastically with the inclusion of outliers. It's very sensitive to outliers because we're talking about the spread of data. Good. I have a quick question for you just to kind of recap what we talked about last Wednesday. When we see this notation, X bar, what does that mean again? What does that represent, X bar?
The mean?
Yes, the mean. This is the sample mean, right? So I'm going to write sample mean, which by the way is the same as the average. So you can write that out if you'd like. The arithmetic average. We know that N is the sample size, right? How many items are in our sample? And I have that written here. N is the sample size. You can underline it, you can highlight it if you'd like. The other piece to note is that X by itself, does anyone remember what this X by itself represents? We saw this. It represents your raw data value. Okay, X by its lonesome represents your raw data value. And lastly, what does this fancy letter here represent? You can look back in your notes if you're unsure, but what does that mean?
The sum of all the values?
Yes, the sum of all the values. So to find the variance, you're going to take each raw data value and subtract the mean. Once you take each raw data value and you subtract the mean, you're then going to square each of those values. Once you square them all, you're going to add them together. After you add them all together, then you divide by one less than the number of items you have in your set. That's what this formula says.
So you do the sum of all the values in the parentheses?
Yes, you essentially will take the sum of all the squared differences. And we're going to end up making a chart in order to do this by hand. After we try maybe one or two, we're not going to rely on our own calculations for this kind of thing. We will just use statistical software to do that. Okay, and we'll talk about that in the future. Beautiful. I just wanted to introduce you to what this is saying, because I think that's going to be really helpful if you have an idea of where you're going. Oh, each raw data value, subtract the mean. Those differences, square them. Add all of those squared differences together, and then divide it by one less than the number of items in your set. That's for the sample. So this is sample variance. This is not for the population. Population variance has its own notation, as does the mean. Cool. Let's turn the page. Standard deviation. Okay. First things first, standard deviation is the square root of the variance. We talked about this. Okay, if variance is s squared, then if we take the square root of s squared, guess what? It gives us s, and s is the standard deviation. It measures how much a data value differs or deviates, deviates, I almost wrote deviation, deviates from the mean. Okay, standard deviation measures how much a data value differs or deviates from the mean. The formula is super similar to what we just saw for variance. The only difference is there's a big old square root there. We still take each raw data value and we subtract the mean, then we square all of them. We add that entire list up, and then you divide by n minus 1, or 1 less than the number of items in your set. Once you have that result, you then take the square root. That's what gives you the standard deviation. I put a little blurb here for why do we divide by n minus 1, because it's not really all that intuitive. So would somebody volunteer to read that little blurb? Why do we divide by n minus 1? Go ahead. Sam,
When we divide by,
go for it, go for it.
when we divide by n, we actually obtain a bias estimate of the population parameter, variance or standard deviation. Our estimate will naturally be smaller if we divide it by n minus 1. Dividing by n minus 1 will give us a larger, unbiased estimate of the true population variance. Check out this simulation created by Khan Academy, proving that dividing by n minus 1 gives us the best estimate of the true population variance.
Perfect. Thank you so much. When you get a chance, if you're, I mean, I'm pretty nerdy, so I like this kind of stuff. If you are nerdy as well, or you're just very intrigued about why n minus 1, go ahead and open your PDF in Lumen, and then you can click this link. You can click it from right inside Lumen, and that'll open up that page where it kind of describes why do we divide by n minus 1. It gives you a nice visual that shows you it's a better estimate of the true population variance. Because remember, we have a sample, right? we're working with a sample and we're trying to map out these statistics related to the population. We're trying to model what the population looks like by using a sample. So we want to make sure that our estimates are as close as possible. We want to minimize our error every time that we run statistics. So it's going to be really helpful, I think, as a visual to take a look and why is this the case? Why do we divide by n-1? Check it out. It's pretty cool.
So we're only worrying about sample standard deviation, not population standard deviation.
Oh, we'll do both. We'll
Oh,
definitely,
okay.
yeah. For right
Okay.
now,
So this is sample, right?
yes, yes.
Okay.
Absolutely. Good. And you'll know that you're working with the population variance or the population standard deviation when your notation looks like Greek symbols. And I mean literally. So like the mean is that mu symbol that I showed you. And then standard deviation is like a sigma. It looks like a 6, but with like a flat top. Actually, I'm just going to draw it for you. That way you have it so you can see it. Nope. Population parameters, right? Because these are numerical values that describe the population. This symbol, and if you want, just look at the screen first for a moment so I could draw it for you. You can see like the pen strokes. So take a look at the screen just for one moment. That's the Greek letter mu, and this represents the mean, which is the average, right? For a population. It has a longer tail in the front. It looks like a U just with a tail in the front. And then for standard deviation, if you take a look at the screen once more, it has like a flat top and then it swirls. So it almost looks like the 6, but like it fell over. And this is standard deviation. If we want to note variance, what would I have to apply to this symbol to go from standard deviation to variance? What is it missing to become a variance?
Squared symbol.
The squared symbol. Perfect. That's exactly correct. So put a little 2, the squared symbol. Now we have variance. Beautiful. That's the set of notation that you're going to use for population parameters, which is nice because then we can easily differentiate. Am I working with a sample? Am I working with a population? Okay, cool. Excellent. Let's turn the page. All right, we are going to actually calculate the standard deviation by hand. Notice that I've got small sets here because otherwise it would take forever and I don't want to do that. Okay, so the following data ages was obtained from a study session at MCC. Find the mean and standard deviation for each data set. We're going to start by calculating the mean. Go ahead and punch this into your calculators, everyone. Oops, I'm typing this in wrong. And calculate the mean first. Don't say it out loud. Go ahead and write it down on your papers. And then when you are ready, type that into the chat. Let's get some activity going. Send it to me privately in the chat. Thank you, Nick. Anthony. Abby, finish that off by dividing. Ava, finish that off by dividing. Good, Chenge. Perfect. Thank you, Grace. Thank you, Abby. Sam, make sure you add your values and then divide by the number of values you have. Thank you, Ava, Holly, Angelica, Nicole, Magnifique, Jerry, Abby, Leah, Colleen, Emma. Cool. So we take our values, 46 plus 55 plus 50 plus 47 plus 52. Please press enter first. Otherwise, your calculator is not going to understand what you mean. It's going to only divide the last number by 5, but we want to divide the sum of the entire set by 5 since you have 5 values. So your mean for this sample is 50. Very cool. All right, let's calculate standard deviation. So again, X, and I'm going to keep writing this. No worries, Abby. I'm going to keep writing what these mean because it's helpful and because I really want you to get comfortable with this idea. So X represents our raw data value. And the first column is going to be just you listing those values. So we have a 46, we have a 55, we have a 50, we have a 47, and we have a 52. Okay, those are the raw data values. You simply list them in the chart. You're probably wondering, do they have to be in order? Clearly they don't. It's helpful, but it really doesn't make a difference because either way you're going to sum the entire column eventually. So I wouldn't even worry. Next, we want to do raw data value minus the mean. Raw data minus the mean. So for your first one, your raw data value is 46. The mean is 50. 46 minus 50 is a -4. If you want, you could even write down how you got this. You could just do a little 46 minus 50, right? For this next one, we've got 55 minus 50, the raw data value minus the mean. So we have 5. For our next one, the raw data value minus the mean, that leaves us with 0. 47 minus 50, that's going to leave us with -3. And then 52 minus 50 is 2. Any questions for me so far? I just want to make sure that I'm going at a decent pace. Awesome. Now remember in the formula, we discussed the fact that we are then going to take the square of each difference. So all we're doing here is we're looking at these values, right, which is x minus x bar, and we're just going to square it. Please be careful. I want to show you something with your calculators because I don't want you to make this mistake. I know that I'm squaring a -4. So let's say that you would prefer to punch this into the calculator. That is not what you actually have on that sheet. So notice if I take -4 like this, written this way, and I square it, I get a -16. That's a problem. Because notice that we have parentheses around that difference. So what we actually mean to say is that we take that value, that difference, and we square it. So in our calculators, please use parentheses or don't include the negative at all. Because when you square a negative, it becomes positive. So if it's going to be helpful to you, you don't have to type in parentheses -4 parentheses squared. Just type in 4 squared, okay? Or just drop the negative. You're never going to have a negative value in this column. This column will always result in positive numbers all the time, every time, because you're squaring your values. So go ahead and write down the squared values here in this column. Just take a moment, fill that in. Good. When we fill in this column, you should have 16, 25, 0, 9, and then 4. According to our formula for standard deviation or for variance, let's start with variance. For our formula for variance, we had to sum up all of those squared differences. And then we divided it by n-1. So let's sum this column. I'm going to draw a line here. I'm going to show that we're going to add those up. Go ahead and punch that into your calculator if you'd like. What's your total?
Before.
Yeah,
54.
54. Beautiful. So that total is 54. Let's go ahead and replace the numerator with 54. And then we have 5 values. N in this case is 5, so we're actually going to divide by 1 less, so we're going to divide by 4. And that's going to give us 13.5. So the variance, and I'm going to sneak that in, I'm going to sneak that right here. The variance is 13.5. One last step to find standard deviation. All we have to do is, would somebody volunteer that info? How do you find standard deviation if you know the variance?
Wouldn't you square root it?
Yes, yes. And this is your sample variance, S squared sample variance, because we're working with a sample. So yes, you're going to square root it. So you have your sample variance. If you square root it, that's what's going to give us standard deviation. So we want to square root 13.5. Let's square root 13.5. And that gives us, let's round to the nearest tenths place. We have 13.5, that's one place after the decimal. So when we take the square root, let's round to one place after the decimal. And that's going to be 3.7. So the standard deviation is 3.7, and that's lowercase s. Talk to me. What can I help with? What can I answer? Okay. So you mean like this is pretty straightforward? Your turn. Oh, go for it. Yes.
Sorry, I just don't understand how you got the raw data value. The
These,
second column,
so the raw,
no, the second one.
oh, right here?
Yeah.
Oh, this, notice what this says. It says, take your raw data and then subtract the mean. So your raw data,
Oh, okay, I see.
good. Always follow the, that's why we like the formula as like our
Mhm.
column headers, because it tells us what it wants you to do. So take that raw data value and subtract the mean. So 46 minus 50. That's why I kind of squeezed it in here, just so you could see. Same thing here, 55 minus 50, the mean is 50, and 50 minus 50, 47 minus 50, and then 52 minus 50. Excellent.
Thank you.
You're very welcome. You're very welcome. Any other questions that I can help with? Okay, hearing none. I actually want you to try number 2 on your own. Study session number 2. You have 5 different values. Go through the same process. Calculate the mean first, then go through the table, go through the same process to calculate standard deviation. Don't overthink it, okay? I'll give you a few minutes. When you're all set, go ahead and type in your solution into the chat. This will probably take you, 3 to 5 minutes. I'm going to pause the recording. Okay, first things first, we calculate the mean. When you add your values up, divide by 5, you find that the mean of the data set is actually the same. It's 50. No worries, Abby. We'll investigate and see what happened. The next thing we're going to do is we're going to list each of our raw data values. We want to be really careful as we do this, just to make sure that we're not accidentally writing, the wrong digit or anything like that. Your next column is the raw data value minus the mean. So we have negative 20, 5, 15, negative 3, and 3. We're then going to square each of these values. That's going to give us 400, 25, 225, 9, and 9. Remember, every value that you have in this column is going to be positive because you're squaring the values from this center column, which means you're going to have positive results. The next thing is we are going to add our squared differences. That's going to give us a total of 668. Is that correct? That is the square differences, the sum of your square differences. I'm gonna scoot this up here so that it's not so cluttered. So we have the variance is equal to the sum of your square differences divided by 1 less than the total number of items you have in your set. So we have 668 over 4. So your variance is 167. So I'm going to go ahead and write that variance. I'm just going to use a notation here, is 167. You're then going to calculate standard deviation. And we calculate standard deviation by simply taking the square root of our variance. So it's the square root of 167. When you punch this into your calculators, you get 12.9. And we'll use 12.9 as our standard deviation. What questions do you have for me? Anything I can help clear up?
When you divided 668 divided by 4, where did you get the 4 from?
The 4 represents 1 less than the number of items that we have in our set. So in our set, we have 5 items, so that's n. So I'm going to write here that n is equal to 5. And you always divide by 1 less because we are trying to create an unbiased estimator.
Okay, thank you.
You're very welcome. The fancy E, don't sweat that. The fancy E just means sum, right? Add them all up. So this says, hey, add all of those square differences. So all we do is 400 plus 25 plus 225 plus 9 plus 9. That's all that that fancy E means. It's just saying, hey, can you add all those up for me real quick? Does that help, Sarn? Okay, excellent, excellent, excellent. Any other last questions for me before we move into the empirical rule? All right, let's turn the page. Here we have the empirical rule. Now we get to finally talk about where standard deviation actually applies. When we talk about normal distributions, we are always going to talk about 2 items when it comes to normal distribution. We're going to talk about what is a mean, which by the way is the same as the median and the mode, but typically we just talk about and focus on the mean. And we also talk about the standard deviation. The standard deviation, that value tells you how far each step you take from the mean. And I'll explain that in terms of the bigger picture, in terms of the normal curve. Think about the fact that with a normal curve, we're going to have quadrants, and each quadrant is separated by a distance that is the standard deviation, how far you're deviating from the mean, either above or below. Let me show you the visual because I think that's going to help a lot. It's going to make so much sense if you're seeing this visual. First off, as a reminder, we know that mu represents the population mean. By the way, this is a diagram that I found that mu could be X bar. It could be a sample normal distribution. It's essentially the same thing. We're looking at the data and we're noticing a normal distribution. So if you saw mu or if you saw X bar, it's the same concept, right? The mean is always going to be the center value. So the mean is here. Think of this line as a number line, right? Think of this line as your number line. So this is kind of going back to that conversation we had about our skewed to the left or skewed to the right distribution. Notice that at the mean, you have your most frequent occurrence. The mean has the most frequent occurrence. And as you get larger from the mean, or as you move smaller or move away from the mean, that frequency decreases, right? So essentially all that's saying is that the bulk of your data centers around the mean. So hence the normal distribution. I want to point out that if you were to cut this normal distribution in half, you will see that there's exactly 50% of the data above the mean and exactly 50% of the data below the mean. I also want you to notice, doesn't it look symmetric? It looks symmetric. We have a 34, we have a 34, we have a 13.5, we have a 13.5, we have a 2.35, etc. So it's symmetric about the mean. Think mirror image here. Okay, now let me talk to you about how we read this. So your center value represents your mean. We have a number line here that will always express from -3 to +3 every single time. And I'll show you because we're going to draw the number line. We're going to draw this normal curve probably a million times. Not even kidding. So Mallory, no worries. You don't have to remember anything like this. It's too much. So essentially what we want to point out is that if you want to move up to 1 standard deviation above the mean, right, a +1, what that reference is that you take the value of your mean and you add a single standard deviation to it. If you want to move 2 standard deviations above the mean, then you're going to take your mean and add 2 standard deviations to it. If you want to find the value that's 3 standard deviations above the mean, then you take the mean and you add 3 standard deviations to it, right? Kind of common sense here. Same thing in the reverse. So if you want to move 1 standard deviation below the mean, notice the way that I said that. 1 standard deviation below the mean. Below is to the left, above is to the right. Below is to the left. Above is to the right. Okay, below the mean is to the left, above the mean is to the right. That might be nice because you have to, when we talk about the language in which we use to describe this, if we said below the mean, we know negative standard deviation values. Here, -1, -2, -3. However, if I'm 1 standard deviation below the mean, that says we're going to take the value of the mean and subtract 1 standard deviation from it. That doesn't necessarily mean that it's going to be a negative number. Let me show you. If you would like, please take out a scrap sheet of paper. I want to show you what this looks like. So we're going to take a scrap sheet of paper and we're going to try to draw our normal curve. And I'm trying to just, oh man, that looks pretty good. That's pretty decent. That's a pretty decent curve. Okay, it kind of looks like crap. The very center is always going to be 0. And we're essentially writing our number line on the horizontal axis. So we're going to go up to 3 and down to -3. This is essentially what our normal curve will look like every time we draw it. So I'm just going to give you a second to draw the normal curve. These values, -3, -2, -1, 0, 1, 2, 3, they are essentially placeholders. So we're normalizing our data and we have placeholders here. How we describe this, so for instance, I'm just going to plot this point here, and I'm going to call that a value 1.5. That value 1.5 means 1.5 standard deviations above the mean. That's what that means. 1.5 standard deviations above the mean. Okay. There's another way to describe this particular location on a normal curve. In addition to saying 1.5 standard deviations above the mean, you can also say the z-score is equal to 1.5. Because this axis refers to z-scores. So there's a dual meaning. They mean the same thing. 1.5 standard deviations above the mean, you know where that's placed. Or we could say a z-score of 1.5. So a z-score of 1.5 is literally where we see 1.5. I know that z-scores mean nothing to you right now. Don't freak out. I promise I will explain what that is describing and where that comes from. Let's look at another one. What if I plotted this point? Negative 2.3. So I plotted the point negative 2.3. We can describe this as 2.3 standard deviations. Which direction?
Hello?
Yes, below the mean. So remember, we're just talking about how to describe these points, these values. 2.3 standard deviations below the mean. That's how you would describe that particular location. But you could also say that the z-score is equal to negative 2.3. Notice that when we describe the z-score, we give the exact value, positive or negative. But when we use a terminology standard deviations, we're saying, are we above the mean or below the mean? Okay, so I just wanted you to see this so you can kind of get an understanding of where all this language is coming from. We haven't done anything with it yet. We just plotted z-scores, right? We just plotted locations. So that's not really helpful to us right now, but I just wanted you to hear that language. So let me put this sheet of paper away for a moment. Now I want to describe to you what this empirical rule is actually showing. Okay, the empirical rule approximates a normal distribution. And what this rule says is if you have a normal distribution, there are some facts that you should consider. The first fact is that 68% of your data in any normal distribution, this is for every single normal distribution, 68% of your data will lie within one standard deviation of the mean. Let's take a look at what that is talking about. Within one standard deviation of the mean. Because it says within, that means above and below, right? Above and below. So I want you to consider within one standard deviation of the mean. So here's the mean. Within one standard deviation means one standard deviation above and one standard deviation below. So I'm looking at these values here, one standard deviation above the mean, one standard deviation below the mean. I'm then going to go ahead and draw a dotted line up. I would like you to do the same thing. What I've done here is I've created a boundary. I'm going to highlight this region. So as we bound from one to the other, notice that I'm highlighting this center region. According to the empirical rule, altogether, that covers 68% of the data. Those percentages will not change. Those percentages will always be the same, regardless of which normal distribution you're talking about, meaning from one word problem to the next. If it's a normal distribution, it follows the empirical rule. Are we okay with that piece so far? That this chunk is 34% of the data and then this chunk is 34% of the data. So within one standard deviation from the mean, it's got to be 34 plus 34, which is 68. Are we okay with that?
Yep.
Sweet. Similarly, 95% of the data are within 2 standard deviations from the mean. So if we're referencing 2 standard deviations from the mean, we are referencing 2 standard deviations above, 2 standard deviations below. We would plot these points, draw the dotted line up. And then instead of just within 1 standard deviation, we're looking at within 2 standard deviations. So we would actually highlight everything that was between those boundaries. So now we're looking at all of this. In which case, if we wanted to determine the percentage of values that lie within 2 standard deviations, you simply add each of these blocks. If you added each of these 4 blocks together, you would get 95% of the data. Okay. And then same thing, if you wanted to reference within 3 standard deviations of the data, now we're taking into account 99.7% of the data, not 100%, but 99.7. So almost all of it is within 3 standard deviations of the mean. I want to add that notation here that sigma, this is our population standard deviation. Let's see this. Take a look at practice problem number 4 below. We're going to use some of this information. Approximately what percentage of the population will be within 1 standard deviation of the mean? Well, we have that answer already, but I would like us just to draw the region. So we're going to go ahead and draw our horizontal line, and then let's draw our curve as best that we can. Remember, these are our notes, so just try to do it as best you can. Always label your horizontal axis, 0's in the center. Go up to +3, down to -3. If we would like to be within 1 standard deviation of the mean, that refers to above and below. So above 1, below 1. Go ahead and draw your dotted line. Because essentially what we're trying to do is we're trying to figure out what region we're referring to. And according to the empirical rule, we know that that is our 34% and our other 34%. So altogether, 68% of the population will be within 1 standard deviation of the mean. I hope you don't mind me abbreviating. Okay, 68% of the population will be within 1 standard deviation of the mean. Okay, take a look at part B. Approximately what percentage of the population would be greater than 2 standard deviations above the mean? This is very interesting. First things first, notice we are referencing 2 standard deviations above the mean. So let's go ahead and draw our curve. Okay, label your horizontal axis. 0, 1, 2, 3, -1, -2, -3. Our location is 2 standard deviations above the mean. That implies I'm going to be here at a +2. This is 2 standard deviations above the mean. The mean is at 0. So let's go ahead and plot our point, draw our dotted line up. And it's asking for what percentage of the population would be greater than that value. would be greater. So we have to shade in the region that's to the right of our dotted line. Take a look at your empirical rule chart on the same page above. What is the percent of the population that would be greater than 2 standard deviations above the mean? And how do you find this? What would you do?
2.5. Wouldn't you add what
Wouldn't you
the
add?
percentage is above?
Yes, perfect.
2.35 plus 0.15% together.
Yes, excellent. So we're essentially here at 2 standard deviations above the mean. We want to know the percentage of values above a standard deviation of 2. So you take the 2.35% block and the 0.15% block and you add those together. So I'm just going to write that down here. You take the 2.35% and add the 0.15%. And we can say that 2.5% of the population would be greater than 2 standard deviations above the mean. What questions do you have for me that I can help answer? Okay, hearing none, take a look at the next page. Look at part
I
C.
actually do have a quick question. How come you didn't like it? You said it was 2 standard deviations above the mean, but why wouldn't it be that area of the what's it called, the 34 and the 13.5?
Ah, great question. So first we have to note the location, right? So as soon as we say 2 standard deviations above the mean, that's why we plot the +2, because that's exactly the location that we're referencing. Then notice it says approximately what percentage of the population would be greater than that. So because we're referencing greater than 2 standard deviations above the mean, we mean shade above. However, if this said what percentage of the population would be less than 2 standard deviations above the mean, that's when we would shade everything to the left. It would be everything in this region. So because of this language, that's what tells us shade above that standard deviation and then find the percentage pertaining to that region.
I have a quick question too. So I was gonna ask the same thing. Why are we not adding it on both sides until I realize it's above? Would there ever be a time or a question where we would have to add both sides?
That's a great question. And actually kind of, what I mean by that is you could be asked to find the region within 2 bounds, and those bounds could be anywhere in under that normal curve. So that's essentially what you're going to end up being faced with. You know, are you finding above, are you finding below, or are you finding the region within 2 boundaries? We're actually going to see that in part D. So let's look at part C, and then I'll show you what I mean by that in part D. Let's turn the page. Approximately what percentage of the population would be less than the mean? Same thing, let's go ahead and draw our curve. Let's label the horizontal axis. Okay, where am I on this number line?
So it would be less than the mean, so it'd be 0 and below.
Yes, perfect. The mean is located at 0. Let's draw our dotted line up. And yes, less than the means that we're going to shade to the left, everything below. Perfect. What percentage of the data does that represent?
Half.
Yes, half. Perfect. 50%. 50% of the population would be less than the mean. Excellent. Now look at part D. Approximately what percent of the population would lie between 1 standard deviation below the mean and 2 standard deviations above the mean? I would like you each to take a second and draw this normal curve, carefully plotting the points that are being referenced. Then, using your empirical rule, try to determine what that percentage is going to be. So just take a few minutes, play around with this. And I wasn't sure if that was confusing at all, but it seems like things are going in the right direction. So yes, add that region up for 81.5% population, percent of the population. Good. Let's take a look at an actual word problem pertaining to this idea. So number 5, the heights of 105th grade children were measured and recorded. The sample was found to have a mean of 57 inches. Okay, the sample was found to have a mean of 57 inches. I forgot, what was the notation for a sample mean? What is this? What's the sample mean notation? I forgot.
Is it the 6 looking thing?
The line over the X.
Yeah, the line over the X bar. Yeah, because it's a sample. So we're flip-flopping, right? We were looking at population and now we're looking at sample statistics. So the sample is found to have a mean of 57 inches. So X bar is 57 inches and a standard deviation of 2 inches. What was the notation for a sample standard deviation?
Just S.
Yeah, just S. Very, very nice. And that is 2 inches. So the standard deviation is 2. Anytime you do this, you always want to jot down the information that you have. Please trust me. Jot down the information you have and then build from there. If we assume the heights are normally distributed, which by the way, you have to be told this in a word problem to know that you're working with a normal distribution. There are so many different kinds of distributions, so you have to be told. We're then asked to draw and label the normal curve to help us find the range of values. So we're looking for the range of values, like what the actual heights are that we would expect to find within 1 standard deviation of the mean. So this is a little bit of a different take. So let's go ahead and mark down option A. Let's draw our normal curve. You are all going to get so good at this. Are your curves getting better or worse?
Worse.
Worse.
How did I know you're going to say that? Every time you draw the curve, it's just worse and worse and worse. Oh, man. For part A, within 1 standard deviation of the mean, we know what this is referencing. 1 standard deviation below, 1 standard deviation above. But do you see how it didn't ask us for the percentage? It didn't say what percent of the population, what percent of that sample lies within 1 standard deviation of the mean. We know that it's 68%, but it doesn't ask that. What it's asking us is to find the range of values, right? Like what are the actual heights? So what we want to consider is that we know that the mean has a value of 57 inches. If we are moving 1 standard deviation above the mean, what this value here represents is that mean plus 1 standard deviation.
So 1 would be 59.
Yes, so this one would be 59 inches because the mean is 57 inches and each standard deviation represents 2 inches. So if we wanted to find 1 standard deviation below the mean, we would take the mean and subtract only 1 standard deviation. So what's the shortest within this range?
55.
Perfect. Beautiful. So for part A, the range of values will be within 55 inches and 59 inches. Do you see what we did here? We took a slightly different approach. This time we weren't trying to find the percentage of children who fell within that height range. We wanted to know what the actual heights were. For part B, we want within 2 standard deviations. I'm not going to draw the curve again because you will all hate me. So I'm simply going to note that this time we're referencing 2 standard deviations above. Hopefully you're okay with me just kind of putting this in the same area. So 2 standard deviations above means you take the mean and you add 2 standard deviations. Cool, right? And then if you wanted below, you're going to take the mean and subtract 2 standard deviations. So mean plus 2 standard deviations, what's the tallest kid here?
61.
61 inches. And what's the shortest?
53.
53. Beautiful. What questions do you have for me as I write down our answer for part B? I'm hearing none, so it sounds like we're okay, unless you're being shy, and I don't want that. Cool, type into the chat within 3 standard deviations of the mean. I would like you to provide the range of values in the chat. And once you do, you're free to leave. Thank you, Anthony. I will see you Wednesday. Thank you, Mike, Abby.
Have a good one.
Yeah, you too. Thank you, Nick, Grace, Sam, Colleen. I'll see you all Wednesday. Beautiful. Adios. Thank you, Angelica, Leah. Yeah, excellent. I will see you Wednesday.
Have a nice day.
Thank you, you too. Excellent job. Yeah, beautiful, Emma. Emma, I would just switch the order, but it's the same thing. Perfect, perfect, perfect. Ava, be careful because we want 3 standard deviations below and 3 standard deviations above. Same thing, Holly. So if we were working 3 standard deviations below, think about taking 57, which is the center, right? That's your mean, that's the height. And then taking away each block of 2. So 57 minus 2, minus another 2, minus another 2. So we're going to take 57 minus 6. So that's going to be 51 inches. And then all the way as high as 63 inches. So that's what we were looking for. Good. Excellent, everyone. I'm going to write down the solution here and you are all free to leave. I will see you all on Wednesday, except for, I believe I'm talking to Stephanie at the end of class, correct? So let me write this down. Yep. Excellent. The range of values will be within 51 inches and 63 inches. And there's your final solution.
It's like -6.
Yes, yes. It would end up being 57 minus 6 to find the lower end, or 57 plus 6 to find the upper end. Remember, each block just represents, in this case, 2 inches. So you're just increasing by 2 inches every time you move up a block. Perfect. Does that help, Ava?
No, because
oh, I have a better idea.
okay.
When we are referencing this -3 value, I'm going to rewrite this because I think it's going to be helpful to see it. Think of the fact that you want to be 3 standard deviations below the mean and 3 standard deviations above the mean. So mathematically, that means we have our mean and we're going to subtract 3 standard deviations. And then we have our mean, and we're going to add 3 standard deviations. So that's essentially what that's saying here. So we've got our mean, which is 57, minus 3 standard deviations, and each standard deviation is 2.
Oh, okay, I didn't do that.
No, that's okay. And sometimes it's helpful to see it using the notation and then filling in those values, because we know the mean and we know the standard deviation. So Ava, from your perspective, I think writing down the formula is going to be hugely beneficial.
Yeah,
Awesome.
good now. Thank you.
Oh, Chenny, got it. My bad. I misheard you earlier. Thank you for correcting me. I really want to say it right. Awesome.
Do we have anything else due for class?
Not right now, not yet. I mean, you could take a look at some more of the Unit 3 stuff, and you should, but we'll assign homework on Wednesday.
Okay, thank you.
You're welcome.
I have a question.
Yes.
So the formula you just made would be 66.
Yes,
Okay.
like above and below. So yes, it's a combined total of 6 inches. So remember that your starting point is your mean. So it's your mean plus the 6 inches, and it's your mean minus the 6 inches.
So that would be the mean, 66. That's the mean.
No, your mean is the center of the data. Your mean is
Okay.
57 inches, and that's what we were
I am
here.
I am so confused because I got 63, but where did the 66 come from?
There is no 66. So 63 inches is correct.
Oh, what about this formula that you just created?
This is 57 plus 3 times 2. This just means your mean plus 3 standard deviations. So it's 57 plus 6, which is 63. So you were right, 63 inches.
Okay. All right, I see.
Beautiful.
Oh, so I see, because I did what I did was 57 I think, let me see, plus 3 and then square root to the 2, which gave me 66.
Okay. Be
Yeah.
careful, because the standard deviation is just 2 inches.
Okay, I
And
see
by
now.
moving over 3 times, you're saying 3 groups of 2. So it's your
Oh.
57 plus 3 groups of 2. If we were going reverse below, then it's 57 minus 3 groups of 2. And that's how we get the 51 inches.
Okay.
Beautiful.
Thank you.
I'll-
Very
I'll see you. I'll see you at 12:30 today.
Yes, Surgeon, I'll
All right.
see you at 12:30. Perfect.
Okay.